Hello everybody, this is Kunal Mehta from Make Me Scientific, and in this video I am going to very easily derive with the help of simple calculus the maximum power transfer theorem. So let us understand first of all what maximum power transfer theorem is. So here we have a battery. So this entire dotted part is entirely the battery. So the EMF of the battery is this E, and this small r is the internal resistance, and we are connecting this battery to an external resistance R. Now, as a result of this, some current I is going to come out of the circuit, and that current is going to flow through this external resistance R. So the power generated across this external resistance is I square times R. And we want to obtain a condition wherein the maximum power is generated across this external resistor. So we know that power across the resistor is I square times R. So basically what we are supposed to do is we are supposed to set the value of capital R such that we get maximum power across the external resistor. Now the total current flowing through the circuit is equal to capital E divided by R plus R, because the internal resistance as well as the external resistances are in series connection. So the current coming out of the battery is equal to the total potential difference divided by the total resistance. So I'm going to plug in this value of I in our equation of power. So power is equal to EMF upon R plus R the whole square times of capital R. All right. Now, if we want power to be maximum, then in that case, the first order differentiation or the first order derivative of power with respect to a variable quantity, wherein in this case EMF is constant, small r is also constant, because for a given cell or a battery you have a constant value of small r and EMF. So the variable is R only. So you are supposed to vary capital R such that you get the maximum power. So dP by dr should be equal to 0, because in maths we know something that when something is maximum or minimum, its first order derivative becomes 0. So that means d by dr of this entire term, that is EMF, upon R plus R, right, the whole square, times R, this whole part, should be equated to 0, right? But I'm going to solve this first, and I know that EMF is constant, so I'm just going to pull out E square common, and then I'm going to write down d by dr of capital R upon R plus R the whole square. See, I'm not going to use the division rule. That is actually, a little bit difficult for the students to do that. So I'm simply going to say EMF square, then d by dr of, I'll write two functions. One is R plus R raised to minus 2 multiplied by R. Because the product rule is very easy, right, for to apply. So I'll just write the next step, that is EMF square, then the differentiation of first, and then R, the second one, is to be taken constant. So that means you please note, I'm just going to write down the rule of differentiation over here. Suppose d by dt of x times y, that is equal to x dy by dt plus y dx by dt. So that means I'm going to take one function as constant and the differentiation of the another one. So in the first part, I'm going to take capital R as constant, then d by dr of R plus R raised to minus 2, and then in the plus, the second part says that R plus R raised to minus 2 has to be taken constant, and then d by dr of R. Correct? So stepwise I'm going a little bit slow, okay? So that means in the next step, this is E square, then I get R. Now we do know the fact that d by dx of x raised to n is equal to n x raised to n minus 1. So here also R plus R, small r is anyways constant. So this will be R plus R, capital R, minus 2 minus 1 times this minus 2 will come in front. All right. So this minus 2 will come here, and then raised to minus 2 minus 1. Okay. And then for the next part, this is R plus R whole raised to minus 2. D by dr of r is simply 1. Alright, so what we are going to do is we are going to simplify this one, EMF square, then this becomes minus 2 capital R multiplied by, I'm just going to write down 1 upon r plus small r raised to 3, because this is minus 3, when it goes down it becomes plus 3. Okay, and over here I am simply going to write down 1 upon r raised to plus 2. Now this term has to be equated to 0, because for maximum power transfer the first order derivative has to be kept as 0. So dividing both sides by E square, EMF square, so simply this part will go off. So what am I left with? I am being left with minus 2r plus small r the whole cube plus 1 upon r plus r whole square, that is equal to 0. I'm going to transfer this on the other side. So I'll get 1 upon r plus r the whole square, that is equal to plus 2r plus r the whole cube. So this whole part will get cancelled with the cube, and I'll be only left with r plus r. And on cross multiplying, I'll get r plus r is equal to 2r, and shifting this r on that side, I will get r as capital R as small r. So the ending statement is, when you keep this internal resistance value, right? When you keep this internal resistance value, small r, equal to that of the capital R, you will get the maximum power across the load. So I hope guys this was a little bit easier for you, but I must say to all my viewers that you should write this derivation and at least twice, right? The differentiation part is easy, but for some of the students it might be difficult. Write it down, you will understand. If you have any doubts, please do ask your doubts in the comment section. Thank you very much for watching the video.